Welcome back, everybody, and welcome to our first encounter with the variational quantum eigensolver. And that's the algorithm which is going to be the main algorithm which we will discuss in the first project. So this lecture is a lecture where first of all, we would like to quickly remind you a little bit about what we did last week. And this is about the Pauli gates, the one-qubit Hamiltonian, which we rewrote in terms of Pauli matrices. So we will just give you a quick reminder. So the material is contained in the slides from last week, but you will also see parts of it in the slides this week. Then, after we've gone through that and we have given a presentation of the variational quantum eigensolver, we will also look at the two-qubit Hamiltonian and how to encode them. And we are also going to look at project number 1, and in particular, the exercises A to D. Now, if you move on a little bit and take a look at the material which we have in the at the GitHub address, there are several notebooks on parts A to D in project 1. So in a certain sense, there is a kind of almost solution. It doesn't contain everything you need to do, and I will come back to that. But hopefully this is something which you can use in order to get started with writing your own program for the variational quantum eigensolver. So the textbook by Hunt has some discussions again about these 1 and 2 qubit gates, which we are quickly going to remind ourselves a little bit about. And then the VQE algorithm is also discussed in section 6.11. But we are going to go through many of the details today, and also next week. We will continue this discussion with relation to project number 1, both this week and in the next 2 weeks. So if you haven't had time to do so, take a look at the Jupyter notebooks. We are going to discuss them today. And you will also find examples on how you can run the exercises for the 1 qubit Hamiltonian, which is a 2x2 matrix, and the 2 qubit Hamiltonian, which is a 4x4 matrix. You will find examples on how you can implement them in Qiskit as well. And then, in addition, run it on IBM's quantum computers. So to quickly remind you, last week, one of the things you will find in the material from last week is an example on how to get started with you setting up an account on IBM's quantum computers. So you can access, typically for free, a 127 qubit machine. Now, these machines are, when you run it for free, you will obviously have to wait sometimes in a queue. So sometimes it can take longer times, and sometimes it can take shorter times. So this was the roughly what we are planning to do this week. There's going to be a lot of discussions on and off with Jupyter notebooks and the slides, but we will also jump into the whiteboard now and then just to remind ourselves about some technicalities. So last week, we actually discussed how to rewrite this 1 qubit Hamiltonian in terms of various 1 qubit gates. And this is essentially where we will start discussing the variational quantum eigensolver. And after that, we will move to the 2 qubit case. And next week and the week thereafter, we will introduce a Hamiltonian, which some of you have encountered before if you've taken a course on many-body physics, and that's the so-called Lipkin Hamiltonian. And the reason why we focus on that specific Hamiltonian is that it has an easy way to transform a general two-body Hamiltonian in terms of Pauli X, Y, and C matrices. And this is something which we will discuss during the lectures next week. So let's quickly remind ourselves about these gates. So when we are setting up a computation on a quantum computer, essentially what we are doing is a set of unitary operations in the space which is defined by our Hamiltonian. And these operators then evolve an initial state. And after some time, we are going to perform a measurement. And this unitary nature preserves the norm of the state vector. It ensures that probability sums to 1. And Since not all gates correspond and observable, they may not necessarily be Hermitian. But the gates which we saw last time, they are essentially all Hermitian gates. So a quick reminder of things which we discussed last week. The famous Pauli gates are the gates which we will see again and again and again. And this 2x2 Hamiltonian, which we introduced last week, is something which we can translate into a 1-qubit Hamiltonian in the basis of the states which are eigenstates of the Pauli Z matrix. And these are the famous qubit 0 and qubit 1 states, which we have seen from the beginning of the semester. So these are the famous matrices which we introduced last week. And then we know that this Pauli X gate, or the Pauli X matrix, which is known as the NOT gate, it flips the state. And the same happens with the Pauli Y gate, that also flips the bit and multiplies the phase by this imaginary number I. And the Pauli Z gates multiplies only the phase of the qubit 1 state by a factor of -1. And these are the states which we use as computational basis states. So one of the things which I will step you through in the Jupyter notebooks is also the way you would initialize your coding by setting up and defining the different 1-qubit gates and the 2-qubit gates, which we are going to use for the 2-qubit system. So essentially, the computational basis which we look at for 1 qubit is qubit 0 and qubit 1, and these are eigenstates of the Pauli Z matrix. That means that when we have a Hamiltonian which also contains Pauli X and Pauli Y matrices, we will have to transform these Pauli Y and Pauli Z X matrices into a Pauli Z matrix so that we can make a measurement in the computational basis. Another famous gate, which we are going to use again and again and again, for the 1-qubit case, this is the gate which now allows us to make a superposition of the state 0 and 1. So when the Hadamard gate acts on qubit 0, it gives us a linear combination of qubit 0 and 1 with a factor of 1 over square root of 2. And if it acts on qubit 1, then it simply has a phase of -1 in front of qubit 1. So this is a gate which we are going to use again and again when we are setting up a system where we have initialized the system, typically a qubit 0, and then we let the system evolve with a Hadamard gate, and we have a superposition of the computational basis states. So this is a state which becomes now a typical example of how we will construct more complicated states later. And when we have 2 qubits, we saw last week, and we're going to quickly remind ourselves about that, we could then introduce a so-called 2-qubit gate, which is called a CX gate or C0 gate, where we then could, when we have made a superposition of the first qubit, we could then entangle the other qubit with the first qubit and create a so-called Bell state. We are going to look at this again. Now, there are some other famous gates. The phase gate, or the S gate, as it's often defined, it has I for the second diagonal value, which again corresponds to us having the exponential with argument I times an angle of pi half. And this has also these states here as eigenstates, except that the eigenvalue here is, in one case it's 1 and in the other one is I. Secondly, it has an inverse, and it's known that the S, the Hermitian conjugate of the gate, when it this applies an I phase shift to the state 1, whereas it leaves the state 0 unchanged. The other gate, one of the famous gates, which we are going to encounter again and again, and this is one of these gates which allows us to entangle a 2-qubit system, which can be initialized in the state 0, 0. And this is the C0 gate. So it when it acts on the first qubit, so the 0, 0, to quickly remind you of that, that is a tensor product of a qubit in system A in state 0 and a system B in state 0. So we write it in this compact way. And this state 0, 0, 0, 1, 1, 1, and 1, 1, which we have here as computational basis states, they are orthogonal to each other. And this is the operation which we get when we operate with a C0 gate. And you see now that when the first qubit, which is then being acted by the upper part of the C0 gate, as we call it, or matrix, where the upper part, the first 2 by 2 block, acts on the first qubit. This leaves the first qubit unaffected. But if the first qubit is equal to 1, then it changes the second qubit to a 1 if the second qubit is in state 0. And if it's in state 1, it changes it to 0. So we also have the swap gate, which is another gate which we will see again and again. So I'm going to now just switch just quickly over to the whiteboard and give you an example from last week where we used these 1 and 2 qubit gates to set up a so-called Bell state. So let's just quickly switch back to the notebook. But before we do that, I just wanted to say that for what is going to come now, when we have a more complicated system, like when we're going to have 2 qubits, we will get chains of 2 Pauli matrices, or the identity matrix. If we have 4 qubits, we will get chains when we rewrite the Hamiltonian as a string of the different Pauli strings. So it often means that when you read it like this, the first matrix here applies to the first qubit, the second one applies obviously to the second one, etc. So and we have put these labels 0, 1, 2, and 3. So we have a kind of ordering where we start with qubit 1 to qubit 4, from the left to the right. And the Hamiltonian is often rewritten or decomposed in terms of Pauli strings, as they can typically, as this is easily implemented on actual quantum computers. So let's take a look at the example which we looked at last week with the implementation and generation of the Bell state. So let's just quickly do that and switch to the whiteboard. So as a part of the reminder from what we ended up doing last week. So the thing which is nice with these gates is that they allow us to set up in a very intuitive way the kind of physical operations which are taking place. So last week, one of the cases which we looked at, if we had a 1 qubit gate, so we could have some initial state, which we label by psi, and then this could evolve to a psi prime state. And we would, in a generic way, we would write this in terms of G, which could be some gate operation, and this is a unitary operation. So G acting on psi gives us the new state psi prime. And we would typically write this as a diagram. So we have the state psi, we just write this gate G, which we have left unspecified, and this gives us a state psi prime. So a typical example was us initializing the system in the state 0. And then we could have, as an example, we could have the Pauli X gate. And we know that this one is a gate or an operation which changes our initial state in state 0, and it changes that to a state 1. So that was an example of what we last week called for a NOT gate. This is the equivalent of a classical NOT gate. So this is a very, very typical example of how we would depict the operation of the operator G, which is normally a unitary operation, and when it transforms an initial state into a final state. And then we can obviously make measurements in between or at the end of all these operations. So if we now look at the 2 qubit state, which we discussed last week, let me just quickly remind you of the Hadamard gate, which you also have in the slides here. So the Hadamard gate is, for a 1 qubit system, is given by this simple operation here. And that means that when we act with the Hadamard gate, as you also have in the slides, with an initial state 0, this gives us a superposition of the two computational basis states 0 and 1. Now we will depict this one. So this is obviously our new state. So this will be the state psi. That's if we want to keep this in a generic way. But let's now just rewrite it. So we would have a state 0, and we act with the Hadamard gate, and then we end up with a linear superposition, which is this state here. Now, what we could then do, since we are getting a little bit ambitious here, we could now move to 2 qubits, and we could initialize our system in terms of 2 qubits, which are in the state 0. So this could be two isolated systems where we know exactly that we can prepare the system in qubit 0 for one system and qubit 0 for the other system. And that is something which we have rewritten in this more compact way like this. So diagrammatically, this means that we would have a qubit 0 here, and then we have a qubit 0. So this is our initial state. Then what is common to do and you will see this again and again when we are setting up a parameterized quantum circuit, which we are coming to soon, what that means, is that we would typically make a superposition for both qubits. But in this case, or what we did last week, was simply to perform a Hadamard operation on the first qubit. So that gives us here a new state, which we call for psi prime. And this psi prime is nothing but 1 over square root of 2, and it had 0 plus 1, and then it's a tensor product with qubit 0 in the other system. So this gives us a linear superposition. Then what we could do, and this is exactly what we did last time, then we can produce a new state by entangling qubit 0 and qubit 1. So qubit 1 is now in a superposition. And what we could do then is simply to perform this C0 operation. And what happens then is that the first qubit obviously is unchanged because it's 0. So if you now look at what we had here, so this one, the first one gives us 0, 0. And then we have a plus. So this is the state which we have here. So when we perform this operation, it gives us a 1, 0. That's the state which we have, the psi prime. But when we now perform the C0 operation on this state, what happens then is that we get a new state, which we can now label as a psi double prime. And this psi double prime is nothing but the state which we labeled as a phi plus, which is one of the famous Bell states. And since the second state of the first qubit is now in the state 1 due to the superposition which we have prepared with the operation of the Hadamard gate, then we get a new state which, since this qubit is given by 1, so we have 1, 0, with the C0 operation, this changes into 1, 1. So what we get then is a 1 over square root of 2, and then we have 0, 0 plus 1, 1. And this is an example on how we can make an entangled state for a 2-qubit system, where in the beginning, this was just given by a pure product state. So just keep in mind that the beginning state, the initial state which we have, is just a product state. The final state, on the other hand, this state here is an entangled state. So this was a typical example of the kind of examples which we can set up and which are relevant for the first part of the project, where you are going to write a small code which then allows you to, with a given initial state, either 1 qubit or 2, and in particular 2-qubit state, it allows you for the 2-qubit state to set up a so-called Bell state. So that was a quick reminder of what we ended up doing last week. Now, what we are going to introduce now is the variational quantum eigensolver, And this is a algorithm which we will first apply on a simpler one-qubit system. So in the one-qubit system, what we had is a one-qubit Hamiltonian. And this one-qubit Hamiltonian is now given by a Hamiltonian matrix, which is a 2x2 matrix, where we have a matrix elements, H11, H12, and then we have H21 and H22. So I'm using this symbol for the operator of the Hamiltonian in order to distinguish it from the Hadamard gate, which we had earlier. Now, our Hamiltonian is typically given by a non-interacting piece plus an interacting piece. And this non-interacting piece has only diagonal elements. And last week we labeled this as an E1 and an E2 here. And the interaction piece could now contain some explicit matrix elements, V11, V12, V21, and V22. So we're just going to leave these matrix elements unspecified, and you will see that in the Jupyter notebook, we are going to set up some specific examples. Now, this Hamiltonian matrix is something which we could now rewrite in terms of Pauli X and Pauli Y matrices. But and Pauli Z matrices. One thing which is very typical in this kind of problems is that we often try to find a part of the Hamiltonian like this H0, which then can be defines an eigenbasis, and that eigenbasis is actually our computational basis. This means that we would have E1 as an eigenstate with a state 0 and eigenvalue E1. And similarly, we have H0 acting on 1 is given by this E2 times 1, that's the qubit 1 state. So we would say that H0, if we are lucky, we can often define a part of the Hamiltonian, which allows us then to define that Hamiltonian in connection with the computational basis which we have chosen. Now, the exact solution is obviously going to be a linear combination of qubit 0 and qubit 1. So the exact eigenvalue, so this is a 2x2 problem. So the first eigenvalue, if we call that psi1, that will obviously be a linear combination of qubit 0 and qubit 1. And similarly, the second eigenstate is going also to be a linear combination of these two states, but it will have different coefficients. So when we diagonalize that 2x2 matrix, and this is something which we can do analytically, we are going to find in the diagonalization the coefficients alpha, beta, gamma, and delta, and then we can define the eigenstates in terms of the computational basis 0 and 1 here. So this is just pretty straightforward exercise in linear algebra when you have a 2x2 matrix and you can easily find the eigenvalues by finding the roots of the characteristic polynomial. Now, one thing which we did last week, which we are coming back to, is actually the definition of the Hamiltonian in terms of the Pauli X, Y, and Z matrices. But one thing which I wanted to remind you quickly of, which is highly relevant for what we are going to do now, is the representation of a given state on the block sphere. So let me quickly remind you of that, because this is an essential element of what is coming now. So if we look at the block sphere for one qubit, we know that the general state, psi, can be written in terms of angles, which then define a given position on the block sphere. And then we would have a e to the I times phi multiplied with sine of theta half times 1. So one thing I want you to notice here and we are going to look at this again and again in the Jupyter notebooks, is that these coefficients which we obtain from diagonalization, they are now going to be given by these angles, theta half and I or phi here. And these angles, which we see here, are then going to define the parameters alpha, beta, gamma, and delta. So when we are diagonalizing this simple matrix here, and we do it classically, we obtain immediately, since we are using this as our computational basis, we obtain immediately these coefficients. But you could now think of, since we are now looking at a linear superposition of qubit 0 and qubit 1, which is the same thing we have here, this is now just a general representation on the block sphere of one of these states here. So keep this in mind, because this means that when we now are going to make an ansatz for a variational solver, so our variational ansatz for this state psi is now going to be given in terms of rotations of the original states, 0 and 1 here, in terms of angles which define rotations along the x, y, and z axis of the block sphere. So that means in principle that we may have something like this. So we can have a rotation matrix, which we defined last week, which we are coming back to now pretty soon. So we could make a rotation around the z-axis by an angle theta, let's call that 2 here. There could be a rotation along the y-axis by an angle theta 1. And finally, we have a rotation. So these rotations are taking place sequentially. So the first one would be a rotation around the x-axis, then on the y-axis and the z-axis. And we have initialized the system in a state 0. So by performing these operations, we're actually going to obtain a state which is going to look like this. So these operations here are actually physical operations which we can implement on the system. It means that as a circuit, we would start with the state 0, and then we would have a Rx operation of theta 0. There's going to be an Ry operation, theta 1, and then there's going to be an Rc operation with a variable theta 2. And then finally, we have a state psi here, which is our final state. Now, this is a state which we are going to use to calculate the eigenvalues of the system. So we have performed now an ansatz where we have 3 parameters. So let's now just rewrite these parameters in terms of a collective container, which I'm going to call theta. So this theta contains a theta 0, a theta 1, and a theta 2. So that means that what we want at the end is psi of theta. Sorry, not like this. And then we are going to calculate the expectation value, where we have rewritten the Hamiltonian in terms of Pauli X, Y, and Z gates, multiplied with the state here. This is the quantity we want to calculate. Now, these are parameters. So that means that we are not sure whether these are the optimal parameters. So the essence of what we end up doing is an optimization. And we are going to do that for all the parameters, the complex parameters we have, which live in a space with p variables. In our case, we have 3. And then we are just going to optimize this quantity here. Sorry, I was a little bit too fast here. Of psi of theta. And this is going to give us the optimal values, theta hat. And with these values, theta hat, we will find the best representation of the energy. And This is just simply another way of rewriting the variational principle. So we have parameters, theta 2, theta 1, and theta 0. We are going to optimize the energy with respect to these parameters. And this optimization process implies that we will have to calculate the gradient, theta. So this is a vector of this quantity here, which we are going to just label as the energy, which is now a function of these variables theta. And this is a quantity we want to drive to 0. And in essence, that means that we are going to use some kind of Newton methods or quasi-Newton methods to find the roots of this equation here. So we need to calculate the gradients. So in the example, which you're going to see now in the Jupyter notebooks, these gradients are going to be calculated numerically. However, for the quantum mechanical systems, which we are going to look at, we can set up an analytical expression for these gradients. This is not done in the examples which you will see, and this is something which we will leave to you to actually implement in project 1. So as I said, these examples which you will see online, they give you a guidance on how you can set up the Hamiltonian matrix, how you can set up the variational quantum eigensolver, but it doesn't implement in an efficient way the gradients, which you can actually do by setting up an analytical formula. And then it also does not perform the type of measurements which you would run when you run a quantum computing simulation of a given Hamiltonian system. So this, in essence, what you see here is what we end up doing with the variational quantum eigensolver. So we have a ansatz. We are now, for the 1-qubit case, we are going to set up a state on the Bloch sphere where we can initialize the system randomly with some specific angles. We don't know whether these are the optimal ones. And then by the variational procedure, where we need to calculate the gradient of the expectational value of the energy as a function of these angles theta, then through a solution of finding the roots of this equation here, we are going to find the optimal variables theta, which then optimize the energy and gives us a variational minimum. So let's go back to the slides from this week and take a closer look at them again. So let's now dive a little bit into the variational quantum eigensolver and take a look at some of the basic mathematics which we are going to deal with. And then we are going to go back to the Jupyter notebooks after the break and look at how we can implement this for a 1-qubit system first, and then for the 2-qubit system. So the initial algorithm to estimate the eigenenergies of a quantum system was actually something which is called the quantum phase estimation algorithm. This is less efficient because it leads to many more gate operations. And in this kind of noisy quantum stage where we are now, this is something which can become impermissible, not possible to implement properly. So that means that we are looking after an algorithm which then actually becomes a hybrid algorithm, where parts of the algorithm will be implemented on a quantum computer and the other parts will actually be run on a classical computer. And the part which runs on the classical computer is the classical optimization part. So we are later going to discuss the quantum phase estimation algorithm. But then to do so, we need to discuss quantum Fourier transforms, and etc. So if we then were to implement the quantum phase estimation algorithm first, it would take us a little bit more time before we would actually be able to do something. And this is the reason why we focus on the variational quantum eigensolver, which is the kind of present state-of-the-art method. So this QPE is provably efficient. but the number of qubits and the length of the circuits required is too great for this kind of noisy quantum era, which we are in now. So it's normally only applicable to large fault-tolerant quantum computers that likely won't exist in the near future. But these things are just moving swiftly. So we are now getting into an era where we are getting a pretty decent control over noise. That means that probably then one could actually go back to the quantum phase estimation algorithm. But the standard algorithm which is being used, and the one we will focus on in Project 1, is something which leads to a parameterized quantum circuit. So parameterized because we are going to make an ansatz for the wave function in terms of these angles as parameters. So it's a hybrid algorithm. It requires the use of both a quantum computer and a classical computer. It is variational because it obeys the variational principle, and it relies on solving an optimization problem, which in our case implies that we have to find the gradient of the energy as a function of these angles. So clearly, if you have many such parameters, it means that you have to evaluate many gradients. So here we use the variational principle, which means essentially that we have an expectation value. This is the standard Rayleigh-Ritz variational principle, which probably you have encountered when you took a course in linear algebra. And this simply states that the expectation value of this quantity, where we obviously divide by the norm of the function, if the function is not normalized, is equal or larger to the true ground state energy E0. So a given Hamiltonian has, we are assuming that it has a true eigenstate of ground state of the system. So the ansatz is typically chosen to be a parameterized superposition of basis states. So these different rotation matrices, which we have discussed, they actually allow us to perform this kind of parameterized superposition of basis states. And that means that we end up with for the 1 qubit case, we end up with a state which we can then represent on the block sphere. And the reason why I'm spending some time on the 1 qubit case in this lecture here is simply because we can get a lot of intuition from the simulations of the 1 qubit case, because we can visualize the state on the block sphere. And then we can figure out where on the block sphere we are when we have found the optimal representation of the system. So these are the optimization parameters. And as I said in that example, we can then perform 3 rotations, X, Y, Z, and that gives us 3 parameters. And then the expectation value of a Hamiltonian in this specific state, which is parameterized by set of angles, is always greater than or equal to the minimum eigenenergy. And this is what follows now is just a very quick reminder of the variational principle. Because if we have the exact eigenstates, we know that this equation here has to hold. If we have that, we can always expand this new state, as you saw from the examples on the whiteboard, when we looked at the 1 qubit case, where we are now expanding a state on the block sphere. And what we end up with is something like this. And we know that the Kronecker delta here gives us simply the coefficients Cn squared multiplied with the energy. And if we have the exact eigenstate, it will just pick up one of these. And that simply minimizes that we can minimize, it simply implies that we can minimize over the set of angles theta and arrive at the ground state energy through this minimization process. So the basic steps are pretty straightforward, and you will see that in the Jupyter notebooks, which we have here. And that means also that if you look at these Jupyter notebooks, and keep in mind that we want you to write your own codes for the Pauli matrices, the operations you're going to do, the optimization part. When you do that, you prepare the initial state on a quantum computer. Typically, you would prepare the state for the 1 qubit state in the state 0. Then you have to measure this circuit in the various bases, and then you send these measurements to a classical computer. And the classical computer post-processes the measurement data to compute the expectation value which you have here. And then the classical computer varies these parameters according to a classical minimization algorithm. This could be a simple gradient descent, that means the simplest possible implementation of Newton's method, or it could be a quasi-Newton method, or if we can calculate the so-called Hessian matrix, which is the second derivative, if we can calculate that one easily, we can then simply just invert that Hessian matrix and multiply that with a gradient, and then perform the iteration step by step. So this steps here sends them back to step one, and then we continue with a new variational state, new angles, because we've got new parameters through the minimization procedure. And then we continue this up to a given number of iterations till we have optimized the energy here, till we have actually found the best possible parameters. So this picture here, which I took from the article by Tilley et al., which you have a reference to, shows you the typical hybrid approach which we have to deal with. So the blue ones, this is actually the what you might call the traditional computing routines. And then the yellow ones are the quantum parts. So you would have an initialization. It could be a Hartree-Fock basis, a mean field basis if you have that. Or you could simply prepare the system in as a tensor product of just qubit zeros, and where each one represents a subsystem. Then we would typically perform a rotation of every single qubit. So that means that we perform a superposition, obtain that. And then here we entangle the first two qubits. Then we could entangle the second qubit with the third qubit with a two-qubit operation. Keep in mind that if you're doing two-qubit operations, this has to be done 2 and 2 qubits at a time. We can perform a new rotation here. And so this can be made more and more complicated, which means that you have more and more parameters. Keep in mind that these entangling operations don't have parameters. So the parameters are then coming from the superpositions here. But clearly, if we were not to entangle, like we do here with a C0 gate, we will not produce a state which is entangled. It would only be a product state. And having only a product state would most likely not give us the final eigenvalue, the correct final eigenvalue. So essentially, this is what we do. Then we have a rotation to a measurement basis, which is done here. We perform a measurement of the Pauli strings, and then that gives us back the inputs which we need to calculate the observables, because then we have h of theta. We calculate the gradients. Actually, the gradient can be calculated analytically, and we're going to show how you can do that a little bit later. So you can calculate them numerically if you want to, or you can calculate them with an analytical expression. So which means that we have to make two calls to a function where we set up the Hamiltonian of the system with the angle theta j, either plus pi half or minus pi half. So this has to be done for all the angles. So in the example which you saw previously, you had 3 angles, and that means that we have 3 derivatives. And this is then fed back. There's a parameter update. So this is the optimization procedure. So this alpha, for those of you who are familiar with the optimization part, is normally often called the learning rate. You can make approximations to this parameter alpha in different ways. It's simply meant as a way to avoid having to calculate the second derivative. Because if you were to take seriously Newton's equation when you calculate these gradients here and fed them into this expression, which is nothing but you having performed a Taylor expansion to the second derivative, then this alpha is inversely proportional to the second derivative. Since this is a gradient, we have more than just one parameter, then this becomes a matrix, and then you would have, for every iteration, you would have to invert a matrix. So those of you who have studied optimization problems in connection with machine learning, you know that this is actually one of the big bottlenecks. So often what we end up using are some quasi-Newton methods, especially when the system is low dimensional. which is typically the case when we are running quantum simulations like this. And then we would have approximations to these alphas, which are then changed for every iteration. So you see the loop here, where you initialize the system, you have an initial representation of the Hamiltonian. This Hamiltonian is then translated into a set of Pauli matrices. Then we initialize the system, we perform the rotations, we find a new state of the system, and then we perform the calculation of the expectation value for the different parameters. We perform the measurements of the Pauli strings. That gives us new expectation values. And so we feed that one in here, calculate the gradients. This is the classical part, and that feeds in new angles. And then we repeat this till self-consistency. So to have any flexibility, before we take a break now, we go through this slide here, we need to allow for a given parameterization. And the most common one is to simply employ these rotation operations, which are given by these rotation matrices, which we will set up after the break here. And then we apply operations, which then entangle these ones if we have more than one qubit. And then applications of, say, the Y rotation ensures that our coefficients always remain real, which often is satisfactory when dealing with many-body systems. Okay, so let's now stop here. And after the break, we are just going to mention how we are going to perform measurements. So keep in mind that the Jupyter notebooks, which I provide you with, they are not setting up the measurements. This is something you would have to add to your codes here. But you can use these examples as a way to get started with your own coding. So let's take a quick break. Okay, so after we have constructed these ansatz in terms of rotation matrices, then the Hamiltonian must be applied. And the Hamiltonian is rewritten, that's always the case, in terms of Pauli strings. And that's in this terms of this string of Pauli matrices that we're going to perform the measurements. And then to get the expectation value of the ground state energy, you can measure the expectation value of each Pauli string. With this P of I, which you see here, is now a set of Pauli matrices. It could be just be a Pauli X or Pauli Y, but you would have to make then the measurement in your computational basis. So the state psi is now this linear superposition plus eventual entanglements, etc., defining this parameterized quantum circuit. And then when we have found the state here, the parameterized state, then we set up a measurement, and we are interested in these variables W of I. So this F of I is the expectation value of a given Pauli string. And then if we have a simple case where we have converted everything in the measurement basis in terms of Pauli Z matrices, we would then simply collect the estimation is then done statistically. So N0 and N1 as the number of 0 and 1 measurements respectively. And then you can estimate this specific variable F of I in terms of the limit when N goes to very large values. So typically we would run this many times, and we simply collect the number of 0 qubits and the number of 1 qubits. Now, this set of measurements is, as a jargon in the literature, in the quantum computing literature, they're just being called shots. So each Pauli string requires, in a certain sense, its own circuit. And so that means that if we break down the Hamiltonian in different sets of Pauli matrices, we would then have to make measurements on these different sets of the Pauli matrices. So multi-measurements of each string is actually required. So you add the results with the corresponding weights, which typically then are the constants in front of the matrices which we have. And the ground state energy can then be estimated. And then to optimize with respect to theta, then you often use a classical optimizer. So what we are going to look at now first is how we can implement this for a 1 qubit case. So keep in mind that the codes which we have set up, one, they are only setting up the gradients numerically using the applied functions for doing so in any of the classical optimizers which you would call. So this could be some quasi-Newton methods like Niels method, you could have the Broyden method, or you could have this other set of methods like the Kobila iterative schemes, etc., etc. So these are possibilities which are then used in the codes, which you will see, where we just call specific functionalities in the optimizations set up by scientific Python. So let's now switch to the Jupyter Notebook, and let's give you a quick overview of where you find all the material. So if you go to the GitHub address of the course, you also have the link in the email which was sent to you, and you look at the published material for this week, go down to week 5. And if you dive into the Jupyter Notebook now, what you will find is the obviously the weekly slides, which we've been discussing now, but there is also a 1-qubit case, which is this one, and this is the one we will start with. There is the 2-qubit case, which applies to part C and D of project 1. So the single qubit case is essentially a first attempt at implementing the VQE for the 1-qubit case. And then there are 2 codes here, which are actually examples on how you can set up everything using sorry, my network was actually a little bit weak, so it fell out. So let me just bring it up again, the Jupyter Notebook, which we were looking at. So the codes which we are going to look at today are the 1-qubit examples and the 2-qubit examples, which then apply to exercises A, B, and C and D in the project. So the let's now switch to the 1-qubit case. Let's go to that specific notebook. So keep in mind now that in these notebooks, we are not applying a set of measurements. We are simply just running everything classically, but we are calling we are setting up the variational quantum eigensolver machinery, but the gradients are actually being calculated via the optimizer which we are choosing, which is typically a quasi-Newton method. So what we have done here is to set up a general 2x2 Hermitian matrix, which we are decomposing into some constants multiplied with the identity matrix, one constant which is multiplied with a poly X matrix, a poly Y matrix, and a poly Z matrix. Now we can, if we define, for instance, all the matrix elements to be real, we could leave out the poly Y matrix. So our general matrix, so these other constants, they're just real constants. But what we could set up then is, if we want to be very general, we could set up a general matrix like this. So we could have a 2x2 Hermitian matrix, and that means that we would then, if D is not 0, we would have to use also the poly Y matrix. In project number 1, we have put the imaginary part of the Hermitian matrix to be 0, which means that essentially our Hermitian matrix is a matrix with real entries only. So what we would typically do then, if you now look at the way we can set up the Hamiltonian matrix, so we can now define this H of I in terms of A plus B divided by 2, and that would give us this identity matrix. And then if I define A minus B, you will see that this could immediately lead to the definition of the usage of the poly Z matrix. And similarly, if D is defined as this H of Y, the constant, then we can actually rewrite the imaginary part here in terms of a poly Y matrix, and C would then lead to a poly X matrix. So if we now look at the VQE for single qubit, so the brute force way we are going to implement this is to set up a unitary transformation in terms of these Pauli X, Y, and Z matrices. Then we are going to measure this quantity here. We're going to do the optimization, and then the final result is actually the ground state energy and wave function. So keep in mind now that the way this code is set up in an entirely classical way. So you could actually run this on any classical computer, and you could think of it as just another way of finding the eigenvalues of the system. So the first things we need to do is obviously to initialize scientific Python, which contains the minimization part, which is used in optimization. We have some plotting functions, and obviously NumPy. So then, and this applies to you writing project number one in your implementation in your development of project one, sorry for that, you need to set up the Pauli matrices and the identity matrix. So these are quantities or variables which you need to set up. So hopefully this can help you in seeing how you do it if you are a little bit in doubt, although this is pretty straightforward. So you see now just printed out the matrices. And another thing which is useful to test is to see that if you have coded it correctly, that all the Pauli matrices squared are actually equal to the identity matrix. And also another identity which is useful, we discussed several of them last week, is to test, for instance, X times Y times Z, which will simply give you I times the identity matrix. So this is useful when you're now setting up strings of matrices. Then we need to perform the rotations. So the Pauli X matrix, the rotated one, gives us a cosine times theta half. And this is multiplied with the identity matrix. So this is the rotation along the x-axis. And we have an angle theta. We have a similar one for the rotation in the y-axis. This is now the one part, which here has a cosine theta half. So it's given us a matrix, a 2x2 matrix. And there will be one part where the diagonal, because this gives us just an identity matrix. And then we have the part here, which now is a y matrix. Similarly here, this becomes an x matrix. And you see this is multiplied with j here. And finally, we have the z matrix, which now is simply us having these arguments here. This becomes 1, and this becomes minus 1, sorry. This gives 1, and this gives minus 1. Then we have the Hadamard gate, which is given by this. And then we define the quantum state by a rotation around the x-axis, y-axis, and z-axis. And these are just simple tests. And you can see now that the Hadamard matrix comes out as it should be. Then in the Hamiltonian, when we're setting that one up, we're going to first create a general 2x2 emission matrix, because we're going to diagonalize that one. And we are going to compare the eigenvalues with what we get from the diagonalization here. Then we decompose it into Pauli components, and then we can reconstruct this, the eigenvalues from the Pauli decomposition. So you can see now the setup, and this is exactly what you're going to do in project number 1, except that the general case here is, I mean, the matrix which you have in project 1 is a special case of the general case, because we don't have a Pauli Y matrix. So the matrix, when we set it up, this is just the setup. So this H of I, H of X, H of Y here, and H of Z, this simply returns the Hamiltonian in terms of this Pauli decomposition. It has a reconstruction here. It sets up the coefficients. So this gives us back the Pauli matrix as we know, the Hamiltonian as we had. So this creates the general Hamiltonian. And we are just setting this up with some simple parameters. So this is the Hamiltonian which we're looking at. And we see now that what we have done now gives the correct representation of the Hamiltonian. So we give some specific parameters, we construct the Hamiltonian, and then check that this gives us the same eigenvalues. And this is essentially what is done here. And you can see that the Pauli decomposition gives us the Hamiltonian matrix in this form. In matrix form, you have these specific values with the entries which we chose for the parameters. We check that it is Hermitian. We found the ground state energy by diagonalizing, and we found the excited state energy. And this gives us also the ground state wave function and the excited state wave function. And you see now the mixing of the coefficients here. And then you can visualize this on a block sphere, and this is extremely useful. So keep in mind now that the general state, so when we now initialize our initial qubit in state 0, when we perform an operation with these rotation matrices, we are going to generate a general state on the block sphere. And that means that our state is going to look like this, where these are parameters which we need to optimize. So in here, we convert a quantum state to a block sphere. And what we are doing now, after we have normalized it, we just compute the block vector components, compute the angles, and then we make a plot on a block sphere. And that's something which is very useful to actually do, because if you look at this now, you would find the states which we have defined earlier, the state 0 and 1. So state 0 points up, and we normally call that the north pole, and the state 1 is here. And then you can look at the components of the ground state and the excited state, and you see that these are almost opposite to each other, and they're actually orthogonal states. So this will be the projection of these states on the block sphere. So in this specific case, we have some specific angles which then represent the state here. So for a single qubit state, now the user universal, we use these rotation matrices to make a general ansatz. So we generate this new qubit state, which is a function of these three angles here. So we can reach any point on the block sphere. We have three parameters, and this is pretty efficient because it's a standard decomposition which is used in quantum compilers. So here we create the ansatz, prepare the ansatz for the system. So we have first a poly C, poly X, etc. And then we prepare the state. This is done here. We return the state. Here we have some test parameters which we are using. So this is just a set of variables which we choose randomly. So these are the test parameters. This is the test state. This is any state on the block sphere. We check the norm as it should be. And then we visualize the circuit here. This is just a visualization. It's not that important. But then you see that we have, in this case, what we did, we had two RZ matrices. So you can actually check whether that is something which gives you a general enough state. You could also discuss whether it would sufficient to be an Rx and Ry rotation. So I leave that as a small exercise to you to figure out what is the most efficient way of making a general one qubit ansatz. But the way you would write the circuit would be something like this. So you initialize with state 0. You have an rotation around the z-axis, y-axis, and again a rotation along the z-axis. Then we are going to make a measurement because now we have this specific state and we want to calculate these expectation values. So we actually have to make a measurement for each polyterm. So each polyterm here represents a specific circuit where we make a measurement on each of these, and then we collect each of these to find the final eigenvalue. So these parameters HC, HY, and HX and HI, these are just fixed constants. So the quantities which we are interested in are the expectation values of these. So this measures now the Pauli matrices, and it sets up the results here. So we have a measure energy. So this E of I, if you look at these different components, E of I would be this one, E of X this one, and E of Y this one, and same with the E of Z. So the Pauli coefficients are those coefficients which we have set up, just constants in front of it. And then we have a function which now performs the measurement of I, X, Y, and Z. Then, if we now look at that, we have to now set up the expectation value, which comes from this measure Pauli here. We get the contribution, we get the expectation value, and then we simply collect the different contributions here by performing the measurement after we have performed the measurement on these different gates here. So if we now look at the different coefficients which we have now a contribution from the identity matrix, from the Pauli X, Y, and Z, which gives us these corresponding values. So this will then give us the final contribution when we also have multiplied with the coefficient. So this is the measurement we make. These are the coefficients which we have set from the beginning as parameters of the matrix elements. And this gives us a contribution here. And this is the total contribution we get when we now have performed the measurement. And we see now that this is the exact energy here. And the difference is 10 to the minus 16. The optimization, so we haven't implemented the VQE here because we've been using the exact wave function. But let's now look at the single qubit part and the way we are going to set it up. So we have this measure energy part, which we set up here. We set up the optimization part. This is where we use the standard optimization method. This is one of the many ones which are options you can use with the SciPy function for optimize. So this is a quasi-Newton method. And in this specific case, you perform 100 iterations. Now, keep in mind that this method does not use the smarter formula for setting up the gradients, which we are coming back to. We are going to derive that equation a little bit later today. Then it runs simply the VQE here, but it doesn't perform the number of measurements in the typical way. It just sets up one measurement and returns that one. So it gives you it has a starting value for the VQE optimization, and then it continues this iteratively till the gradients are basically zero. And that's essentially the whole procedure which is set up here. So this is the VQE class. Here we run the VQE. So keep in mind again that we are not doing these measurements again and again, and we collect the number of values which we get. This is something which we want you to actually implement. We will also discuss this next week when we are going into more details with the Lipkin Hamiltonian and the explicit setup of the measurements. And when you look at the final parameters here, when you make a comparison, you will now see that after 49 iterations instead of 100, which was set up, these were the initial parameters for these angles. And then you see now that this is the result I get, and this is the exact energy, and this is this variational quantum ground state energy, which is given by this value here. And the absolute error is 10 to the minus 9, which you could say is acceptable. And this is the overlap between the final wave function I have and the exact wave function. And these are the optimal parameters, which we end up with. If you then want to make a kind of visualization of this, you can also visualize both the exact, so you have we exact eigenstates and the VQE states, and both the real part and the imaginary part. And this is in the wave function. We can then set up the exact energies, as you can see here. And these are the contributions from the different measurements of the Pauli X, Y, and Z matrices. Keep in mind now that we are not doing the measurements again and again. So we're simply calculating here I should just keep, I want to emphasize this. So we are calculating just the value of these expectation values by plugging in the ansatz we have for the wave function in terms of the angles, and then simply calculating numerically these different quantities which we have here. This is not the way you would end up doing it, because you would have to transform these Pauli X and Y matrices, Pauli X and Y, in terms of a Pauli Z matrix times some Hadamard matrices. So this is something which we will discuss more explicitly next week. So this is just to set up the basic machinery of the VQE, but where we are cheating a little bit, because the measurements in the code which you see here does not perform the measurement in the computational basis, which is the basis, which is an eigenstate of the Pauli Z matrix. So keep this in mind when you're now writing your own program. This is more meant to give you the overarching view on the VQE algorithm. And next week, we are going to discuss in more detail how you will set up the expectation value of this Pauli X matrix and the Pauli Y matrix in the computational basis, which is an eigenbasis of Pauli Z. I hope this. I hope I have made this pretty explicit, because when you write the final code, you're going to add the number of measurements in the evaluation of these expectation values. And in order to perform the measurement, you have to convert the Pauli X and the Pauli Y to a Pauli Z matrix. So keep in mind that the Pauli X matrix is given by a Hadamard times a Pauli Z times a Hadamard. So these kind of details are things which we will dive more into next week. So I hope you can forgive me for that, because I just wanted to expose the variational quantum eigensolver first. So in a way, we are, in this code, we are actually cheating a little bit. And we're also not implementing the calculation of the gradient of the energy in the best possible way. And now, when we do this, this is just the convergence in terms of the iteration of the optimization algorithm. And if you look at the plots now, if we just scroll down, these are just plotting functionalities. You will see now that after some 20 iterations roughly, then the VQE energy, this is where we started with the initial guess. And then the VQE energy, after some few iterations, converges rather quickly to the exact eigenstate. So keep in mind that we are doing a variational eigensolver, and that means that we are targeting the lowest state of the system. And you can also see the energy error on a log scale. And when you have reached some 50 iterations, you have an error of roughly 10 to the minus 9. And this is the overlap between the exact state and the exact ground state. You can also see how the parameters evolve. And you will see now that in this specific case, theta 0 also needs roughly some 20, 30 iterations. The same with theta 1 and theta 2 as well here. What is nice to look at, if you want to visualize this, is actually a trajectory on the block sphere. So if we now just scroll down here, this is just a plot on how these angles develop as a function of the number of iteration of the optimization algorithm. So you could now see, if you look at this one, this is where you start. This is a starting value. This was our initial guess. We started with some random values. And then we end up with the final VQE value, which is this one with a blue box. And then you have the star here, which is the exact value. And this gives you then the kind of trajectory which are taking as a function of the different iterations. So keep in mind, again, I'm just repeating this ad nauseam, is that the number of iterations is just a part of the optimization part, but you would also need to have a loop over the number of measurements which you're doing. And this is what you will end up doing in an actual implementation on a real quantum computer. You would have to set up the number of shots or measurements, which you then use to calculate a mean value for the different expectation values. So I like this one because it gives you a nice view on the optimization algorithm itself. So then you can look at the specific energy contributions here. And if you look at the energy contributions, this is also nice to look at. When you diagonalize exactly, you know what the different parts of the decomposition of the Hamiltonian should give you. So the blue one is the exact one, whereas the orange one is what the VQE gives, and you see that basically these match each other. And in this specific case, the identity matrix gives a pretty large contribution, and the poly Z matrix also gives a pretty large contribution. But you have some admixture from the different poly X and poly Y matrices as well. You could start with a random initialization, which is typically done. So you would test the VQ with different starting points. We're going to skip this one because I wanted to get back to the calculation of the gradients so that we have an important ingredient for the discussion next week. So this just contains a convergence in terms of random starts here. This is actually not so interesting. And the same with this one, these are just final plots on how things converge in terms of the optimization procedure. So what you have here is the VQE implemented by you setting up the unitary transformation through these rotation matrices, which give you a state on a block sphere. When you have that one, we calculated in a brute force way the expectation value of the poly spin decomposed Hamiltonian, but we do not do the measurement in the basis, the computational basis. We simply calculate brute force the different expectation values, and we add them, feed them to the optimization algorithm, and we find new values of the angles, and then we keep doing this till the gradient is roughly equal to 0. So there are some missing ingredients here. And one of the first missing ingredients is actually the calculation of the gradients. So let me just set this up by going back a little bit to the whiteboard so that we can look at some of the more important details which we need to set up. So let me bring back the whiteboard here. So in this specific example, what we have not done is to calculate the gradient properly. So the gradient in this example, and this applies to the qubit case as well. So the gradient of the energy as a function of the angle theta is calculated numerically by numerical derivatives, is not calculated in the most efficient way. Actually, what we can show, if we now define this quantity here, E theta plus pi half, this is given by the expectation value with respect to the angle theta of this trial wave function, theta plus pi half. And then we have the Hamiltonian, and then theta plus pi half. And if we define the next quantity with theta minus pi half, this is what we are going to show pretty soon now, that this is the expression which we would typically implement for most of the applications of quantum algorithms for finding the eigenvalues. So this is this delta theta of E theta, we are going to show that this is proportional to E of theta plus pi half minus E of theta minus pi half. So this is one modification which we're going to do, because the typical way this is implemented when you call one of the scientific Python optimizers without thinking is that the scientific Python optimizing function will actually evaluate this quantity here by a standard numerical algorithms for finding the derivatives. So this is one missing item. So this is item 1. And then the other item, which we have not taken care of properly in these codes, is the expectation value of these quantities like y and x and z. So for this 1 qubit case, we know that this state on the block sphere, which we produce, is now given in, and now I'm just leaving out the cosine theta halves, etc., is given by these coefficients alpha plus this coefficient beta times 1. And then we know that when we now perform a measurement in the computational basis, which is this basis here, then obviously this one, the Pauli Z matrix, is a matrix which has this as an eigenbasis. However, when I now implement this for the Pauli X and the Pauli Y matrix, these are no longer a computational basis or an eigenbasis of these matrices. So that means that in order to perform the measurement on, for instance, the Pauli X matrix using the computational basis, we would have to rewrite the Pauli X matrix, as we discussed last week, in terms of a Hadamard matrix times a Pauli Z times a Hadamard matrix. So let's look at what this specific expectation value is going to look like when we perform a measurement in a quantum computer. So if you look at this expectation value here, this is psi of theta multiplied with x and psi of theta. Now we can replace that one by setting up this x in terms of a Hadamard matrix times a Pauli Z times a new Hadamard matrix. So that means that what we would have then would be psi of theta multiplied with a Hadamard. And then we take the expectation value here, C, and then we would have a new Hadamard of psi of theta. So it means that the specific quantum circuit for that case changes from what we did in the simple implementation here. So we are coming back to this part in more detail next week. The thing which I wanted to go back to now is first the calculation of this quantity here. And then next week, when we are going to revise this simple single 1 qubit implementation, we are going to rewrite this operation here in terms of a Hadamard acting on the state which we had. So it means that what we are doing now, we take this qubit 0, there is a set of rotation matrices, which I just labeled with an RC, it could be an RY, different angles, and then we would have an RX, depending on how we do it, but then we would have a Hadamard gate here. And then we would have the final Pauli Z here, which we are then going to act on with this state here. So I'm just going to go into more details next week, but now I wanted to give you the expression, the final expression, the derivation of this specific term which you see here. So let's go back to the slides for this week and take a closer look at that one. And this is roughly where we will end this week. So as you can see, this is meant as a way to anticipate what we just discussed now. So these Pauli X matrices will typically be rewritten in terms of a Pauli Z matrix multiplied with, let's say, a Hadamard. And similarly, a Pauli Y matrix can actually be rewritten in terms of a Hadamard times a phase matrix. And then we will have a Pauli Z matrix in the middle here. So this obviously complicates what we are going to do. I'm coming back to this topic here next week, but I wanted just to set up the calculations of the specific setup of the gradients here. So let me just see where, yeah, here it's where we are. So when we are setting up the gradients, suppose now that, as an example, that we are now performing 2 rotations. So we start with a qubit 0, and then we perform a rotation around an angle theta, and then an angle phi in the x and the y directions respectively. And each of these rotation matrices can be written in a more general form as a cosine times gamma half here times identity matrix minus sine minus I times sine, and then the angle, the rotation angle gamma divided by 2 times the explicit Pauli matrix. So if this I here corresponds then to the explicit Pauli matrix which I'm looking at. And it could be any of the X, Y, Z matrices. So there's another important aspect here. It's also easy to see that the derivative with respect to this angle, which becomes important for us, is something which is pretty straightforward to set up an analytical expression of. So it gives you the original rotation times just a Pauli matrix times the angle divided by 2. So this is a useful relation which we are going to use here. Now, actually, I see there's a missing quantity. This is just the Hermitian conjugate here. So what we have is that the derivative of this quantity here, this specific expectation value, is something now which will contain this derivative. So because keep in mind now that this, if you have performed a rotation, and we have a rotation along the x-axis and the y-axis, we are going to use this formula here, which then simply means that when I now calculate the derivative, this plus, I'm sorry, this is missing on the slides here, this is a Hermitian conjugate of this expression. So I would have a Pauli X matrix here, because I have a rotation in the x-axis, and I have a Pauli Y matrix because I have a rotation along the y-axis as well. So that's the first step. Now, this means that we have to calculate 2 additional expectation values in addition to the expectation value of the Hamiltonian. So one thing is the expectation value of the Hamiltonian itself, but the other one is the calculation of the gradient, which is now going to lead to the calculation of 2 additional expectation values. So that adds some more complications to the recipe of the VQE recipe, but it's still doable. And we have an analytical expression for the gradient. So instead of evaluating that numerically, which then can require more CPU cycles, we end up with an explicit analytical expression. And this is the one which we are going to derive, but we will have to do this more properly next week. So in the slides here, you see basically the recipe and the way we would move. But we are going to look into the final details of this algorithm next week. So you have essentially the derivation in the slides for this week, but I see that time is running out here, so we should try to stop. But for next week, we are going to go through the explicit derivation of this quantity. We are going then, after we've gone through that derivation, we are going to look back at the explicit calculation of the expectation values of a Pauli X, a Pauli Y, and the Pauli Z matrices. So the program which you have seen today is actually a too simple program but it contains the basic essence of the variational quantum eigensolver applied to one qubit. So next week, we are going to see how we can set up these expectation values, and we are going to implement the expression for the gradients using the analytical formula. So that means that the codes which you have seen this week, they will be modified next week, and they will be modified so that you will see an explicit implementation of the one qubit and the two qubit case the way it really should look like. So what you have this week was a simplified version, which we are going to correct next week, so that you then have the basic elements of the variational quantum eigensolver. So I hope this allows you to see the wood for the trees, and that the examples which I gave you now, they don't contain the full truth, but they give you a kind of a kickstart on how your code should look like. But then we have to implement the gradients, and we have to perform the measurements in the computational basis. And this is a topic which I want to use the full next lecture in order to develop the equations which we have to implement. Feel free to ask questions. I'm going to stop the recording now. If you have questions, please let me know.